Welcome to this explainer. Today, we are diving into something seriously fascinating. We're going to look at the very core of how artificial intelligence actually thinks, acts, and ultimately solves problems. We're tracking a massive evolution here, watching AI grow from making simple, totally blind guesses in the dark to mastering incredibly complex competitive games. It is a brilliant transformation of machine logic, and I am so excited to guide you through it. So here's our roadmap for today. We'll start with the quest for optimal solutions, move from blind to smart search, look at local search and optimization, tackle solving under strict rules, get into playing games with adversarial search, and finally, wrap up with choosing the right strategy. First up, quest for optimal solutions, the goal of AI. Next, we are moving from blind to smart search, gaining direction. Okay, so this is the very first massive leap in how machines think. Imagine an uninformed search, like breadth first or depth first, as you wandering through a giant maze in pitch darkness. You're just bumping into walls, exhaustively checking every single path without a clue where you're going. But then we get to informed search methods, like A*. Suddenly, boom, someone hands you a flashlight. The AI uses real environmental clues to actually calculate the smartest path forward. And you know what that flashlight actually is? It's called a heuristic function. This is absolutely the secret sauce of an informed search. Instead of kicking open every single door in a long hallway, it acts as a mathematical shortcut. It's kind of like the AI playing hot and cold. It gives an intuition that says, hey, getting warmer. This guides the system straight toward the optimal solution, saving huge amounts of time and computing power. Moving right along to local search and optimization, adapting to the environment. Well, sometimes an AI doesn't need to map out the entire universe of possibilities, right? It just needs to optimize what's directly in front of it. Take hill climbing search. It basically just steps up to neighboring states until it hits a peak where no move makes it any better. Then there's simulated annealing, which actually borrows from metallurgy. It mimics the heating and super slow cooling of metal to find absolute structural perfection. And genetic algorithms? They pull straight from biology, using the principles of survival of the fittest to breed better and better solutions over successive generations. Pretty wild, right? Next up, solving under strict rules, constraint satisfaction. I know constraint satisfaction sounds incredibly academic, but it really boils down to classic, totally relatable brain teasers. Think about the crypto-arithmetic problem, where letters have to be uniquely swapped with digits to balance an equation perfectly. Or the classic water jug problem, trying to measure an exact amount of water using jugs with totally random capacities. Or even graph coloring, where adjacent regions on a map absolutely cannot share the same color. By navigating these uncompromising rules, the AI learns to creatively solve problems even when its hands are totally tied. Now for the really fun part, playing games, adversarial search, competing against humans. This right here is the climax of AI's evolution. It's no longer just solving puzzles alone in a room. It has an active opponent. Step 1, evaluate the board. Step 2, anticipate the enemy. Step 3, execute what's called a min-max search. Basically, the AI plays out all future moves to intentionally maximize its own gains while actively minimizing yours. It is quite literally thinking several steps ahead just to set a trap for you. But here's the catch. Thinking that many moves ahead requires a staggering amount of processing power. Enter alpha, beta, pruning. This is a brilliant little trick used during that min-max process. It literally prunes or trims the fat off the decision tree. By letting the AI completely ignore totally useless branches of moves, it decreases the number of nodes the algorithm actually has to evaluate. It saves a ton of computational time, which means the AI can calculate way deeper and strike a whole lot faster. So, with all these incredible tools in the toolkit, let me ask you, how do you actually select the absolute best searching method? We are shifting gears right now from theoretical game playing into practical, real-world application, which brings us to choosing the right strategy, applying what we've learned. Because just knowing the theory isn't quite enough. True mastery means getting your hands dirty with open-source tools. You've got to push into self-learning advanced stuff, like the memory-efficient IDA* and SMA* algorithms. That is what takes your practical application to the next level. It's all about pairing that foundational heuristic knowledge with modern toolkits to solve actual problems where memory and processing power have hard, real-world limits. We've tracked the whole journey from blind, aimless guessing to highly strategic, opponent-crushing logic. You've seen the mechanics behind heuristics, local optimization, constraint satisfaction, and adversarial printing. So I want to leave you with this final thought. Now that you actually know how these algorithms think and adapt, what incredibly complex problem are you going to ask AI to solve next? Thanks so much for joining me for this explainer. Keep exploring, and I'll see you next time.